Now let's talk about chemical bonding. So there are two types of chemical bonding that can lead to two different types of compounds. The first is ionic bonding, which leads to ionic compounds, and the second is covalent bonding, which leads to covalent compounds. In ionic bonding, we have ionic compounds which are crystalline solids, they have high melting point, they conduct electricity when in a liquid or dissolved in water, and they are also mostly water soluble. An example of this would be sodium chloride or table salt that you spray on your food. Covalent compounds, on the other hand, can be solids, gases, or liquids. They have lower melting points, and they're poor electrical conductors when a liquid, and they also don't dissolve in water very well, but if they do dissolve in water, they're also poor electrical conductors. An example of this would be water. So chemical bonding, the definition of chemical bonding is an interaction between the valence electrons of two or more atoms. So just a reminder, valence electrons are the outermost electrons. So recall the octet rule from earlier, where we need a full 8 electrons in the outermost shell to have a stable atom. So that's the basis for chemical bonding. So ionic bonding occurs when electrons are donated and accepted from two atoms. So we'll take a look at sodium chloride. So sodium chloride is formed when sodium donates its 1 electron in its outer shell to chlorine, which has 7 electrons. Because sodium has another shell underneath, that shell will now be the valence shell, and it'll be full because it's already full. Chlorine needs 1 more electron to form an outer shell of 8, so it will happily accept that electron. That'll give us the two ions, the sodium ion and the chloride ion. And because positive and negative charges attract, we're going to attract to make sodium chloride, which is table salt. So just remember, metals always donate 1 or more electron, and nonmetals will always accept 1 or more electron. Covalent bonding is a little different. In covalent bonding, a bond is formed when electrons are shared. So let's take a look at what happens in water, H2O. So oxygen is here with its 6 electrons. Two pairs of them won't be used for bonding because they're already paired up. But this one over here is on its own, and this one over here is on its own. Hydrogen also has 1 electron on its own. So we can make a bond by sharing these 2 electrons. Remember hydrogen, because in its outer shell it only has 1, it needs to complete 2 because it's the innermost shell. So it's happy having 2. Whereas oxygen needs 8, so when it shares with 2 hydrogens, it'll have 8. That'll give us the water molecule. These 4 electrons over here are not bonding, so we just draw them attached to the oxygen. So to better understand chemical bonding, we need to understand electronegativity. So electronegativity is a measure of an atom's ability to attract the shared electrons in a bond. So each element is assigned an electronegativity, which you can look up. It's typically on the periodic table, but some periodic tables don't have it. But you can always find a periodic table that has one. So fluorine has an electronegativity of 3.98, chlorine 3.16, and so on for the others. So the difference in electronegativity is what's important. The difference in electronegativity is just if you have a bond between, say, carbon and hydrogen, you need to find the electronegativity of carbon, subtract the electronegativity of hydrogen, and then you get the delta electronegativity, or the difference in electronegativity. So, depending on our value for delta electronegativity, we can tell if a compound is nonpolar covalent, polar covalent, or ionic. So a difference between 0 and 0.5 gives us a nonpolar covalent compound. A difference between 0.5 and 1.7 gives us a polar compound. A difference of 1.7 or greater gives us an ionic compound. Let's take a look at a couple of examples. The electronegativity difference in the bond between lithium and fluorine can be examined, such as the bond in lithium fluoride, by taking a look at their electronegativities. So the electronegativity of fluorine is 3.98, and lithium is 0.98. The difference is 3, which makes it higher than 1.7, therefore it's an ionic bond and an ionic compound. If you take a look at the bond between carbon and hydrogen, carbon's electronegativity is 2.55, and hydrogen's is 2.20. If you subtract that, you get 0.35, which makes it a nonpolar covalent bond. Between carbon and fluorine, well, fluorine is 3.98 and carbon is 2.55. The difference is 1.43, which makes it a polar covalent bond. So now let's talk about the properties, specifically one property, solubility, of polar and nonpolar compounds. So the polarity of the compound affects its solubility, according to the rule, like dissolves like. That means polar solvents, like water, will dissolve a polar molecule. And nonpolar solvents, such as toluene, C7H8, dissolve nonpolar compounds. So methane right here is drawn as a carbon bonded with 4 hydrogens. Like we said earlier, the carbon-hydrogen bond is nonpolar, so this overall is a nonpolar molecule. It's always a good idea to draw out the molecule before you figure out if it's polar or nonpolar. So because methane is nonpolar, it'll probably dissolve in a nonpolar solvent, such as C7H8 toluene. Let's take a look at fluoromethane, CH3F. So it's the same as methane, except it has a fluorine attached to it. Like we said earlier, the carbon-fluorine bond is polar. So when you have a polar bond, and you draw it out in a molecule, it's nice to have this dipole. So a dipole just points to where the electrons are being favored. So the electrons are favored over here because, like we said earlier, fluorine is more electronegative, and electronegativity is a measure of an atom's ability to attract the shared electron pair. So yes, the electrons are shared between carbon and fluorine, but fluorine attracts the electrons slightly more, so it gets a partial negative charge. It's not a negative charge, but a partial negative charge. So this is a delta minus. And because it's attracting those electrons from carbon, carbon gets a slightly positive charge, so delta plus, and the dipole points that way. So a dipole is just an arrow with a plus on the positive end. So because fluoromethane is polar, because of that bond, it'll probably dissolve in something like water.